The concept of a warp drive, popularized by science fiction like Star Trek, has long captivated imaginations as the ultimate solution for interstellar travel. While still firmly in the realm of theoretical physics, recent advancements and ongoing research suggest that the idea of warping spacetime might not be as impossible as once thought. How warp drive works, theoretically. The most widely discussed warp drive concept is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. It doesn't involve moving a spaceship faster than light through space, which is forbidden by Einstein's theory of relativity. Instead, it proposes a way to manipulate spacetime itself. Warp bubble. The Alcubierre drive would create a warp bubble around the spacecraft. Space contraction and expansion. Within this bubble, space in front of the ship would be compressed, while space behind it would be expanded. Riding the wave. The spacecraft would essentially ride this wave of distorted spacetime, allowing it to cover vast distances at an effective speed faster than light, without the ship itself exceeding the speed of light locally. The occupants within the bubble would not experience relativistic effects like time dilation. Latest advancements in research. While the Alcubierre drive initially faced criticism due to its astronomical energy requirements, research continues to explore its feasibility and potential workarounds. Positive energy models. Recent theoretical advancements are exploring warp drive models that rely on positive energy, moving away from the need for hypothetical, exotic matter, which would have negative energy density. Reduced energy requirements. Some research, notably by NASA physicist Dr. Harold Sonny White, suggests that altering the shape of the warp bubble, for example to a torus, could dramatically reduce the energy requirements from Jupiter's mass energy equivalent to something more manageable, like the mass of a large spacecraft, though still immense. Computational tools and simulations. Scientists are developing innovative tools to simulate warp drive models and analyze the gravitational waves that would be emitted by such devices. Subluminal warp drives. While faster than light travel is the ultimate goal, some research is focusing on subluminal, slower than light, warp drives. Even if they can't achieve FTL, they could still offer significant advantages over conventional propulsion methods for interstellar travel. Connecting to quantum physics. Researchers are investigating how quantum field theory could be adjusted to make warp drives more feasible, exploring how quantum fields interact with spacetime. Challenges and hurdles. Despite the intriguing theoretical progress, significant challenges remain. Exotic matter or negative energy. The most significant hurdle for many warp drive concepts, particularly the original Alcubierre drive, is the requirement for exotic matter or negative energy density. While negative energy has been observed in Casimir effect experiments at microscopic scales, producing it in the vast quantities needed for a macroscopic warp bubble is currently beyond our technological capabilities and our understanding of physics. Causality violation. Some theoretical models of faster-than-light warp drives could potentially violate causality, leading to time travel paradoxes. This is a fundamental concern for physicists. Energy requirements. Even with proposed reductions, the energy requirements for a functional warp drive remain astronomically high, far exceeding any current or foreseeable energy sources. Stability and control. Creating and maintaining a stable warp bubble, as well as controlling its direction and velocity, presents immense engineering challenges. Radiation and tidal forces. Theoretical analyses suggest that powerful tidal forces and intense radiation, for example Hawking radiation, could be present at the edges of the warp bubble, potentially incinerating anything within or around it. The future of space exploration with warp drive. If a warp drive ever became a reality, its impact on space exploration would be nothing short of revolutionary. Interstellar travel. The primary and most profound impact would be the ability to traverse interstellar distances in weeks or months rather than thousands of years. This would open up the entire galaxy for exploration, allowing humanity to visit exoplanets, search for extraterrestrial life, and potentially establish interstellar colonies. Resource acquisition. Access to resources in other star systems could alleviate resource scarcity of Earth and enable the growth of a truly spacefaring civilization. Scientific discovery. Direct exploration of distant star systems would provide unparalleled opportunities for scientific discovery, furthering our understanding of the universe, planetary formation, and the origins of life. Human expansion. Warp drive could facilitate the spread of humanity beyond our solar system, ensuring the long-term survival and diversification of our species. Transforming our perspective. Interstellar travel would fundamentally change humanity's perspective on its place in the cosmos, potentially leading to new philosophies, technologies, and societal structures. While the engineering and physics hurdles are immense, the persistent pursuit of warp drive technology highlights humanity's insatiable desire to explore and push the boundaries of what is possible. It remains a powerful motivator for research in fundamental physics and advanced propulsion systems, even if its full realization lies far in the future.